Welcome to the Groundwater Lab. This week, our activities, content, and assignments will help you be able to do the following. 1. Explore how surface water and groundwater systems interact. 2. Identify pollutions that may contaminate surface and groundwater due to human activities. 3. Analyze potential solutions to surface and groundwater contamination. 4. Become familiar with measuring groundwater depth. 5. Create a contour map to understand groundwater flow direction and pathways. First, we'll start with some background information to provide you context for this week's lab. Water is a vital resource that exists in three forms on Earth: liquid, solid, and vapor. These forms are part of the water cycle, which begins with water vapor condensing in the clouds, falling to Earth as precipitation, and then following various paths such as runoff, infiltration, or uptake by plants and animals. The water then returns to vapor through evaporation or transpiration, completing the cycle. Much like the rock cycle, there is no starting or ending point to the water cycle. The vast majority, over 97%, of Earth's water is saline ocean water, while only 2.8% is fresh water. We rely on two main sources of fresh water: groundwater and surface water. Groundwater is found below the surface, either just beneath the soil or in aquifers, which are underground water reservoirs made of permeable rock. Aquifers hold water for long periods but recharge slowly. Surface water, such as streams and rivers, is more dynamic and transports water, sediment, and nutrients downstream. As a society, we use water for numerous purposes, including cleaning, drinking, irrigation, and power generation. With the global population exceeding 7 billion, our daily water consumption is substantial, making understanding and managing water resources critical for sustaining life on Earth. Groundwater is a vital drinking resource for large populations around the world. It provides a reliable, often clean, and easily accessible water supply, making it especially important in areas with limited surface water resources or infrastructure. In the United States, groundwater plays an important role in meeting the drinking water needs of both urban and rural populations. Approximately 51% of the U.S. general population, or about 170 million people, relies on groundwater for their drinking water. This includes both public water supply systems and private wells. The importance of groundwater is even more pronounced in rural areas of the United States, where 99% of the population depends on it as their primary drinking water source. In many remote areas, groundwater is often the only available option, with numerous rural households and farms relying on private groundwater wells. Groundwater has several advantages as a drinking water source. It's generally clean due to natural filtration through soil and rock layers, making it less susceptible to contamination compared to surface water sources. Groundwater is a portion of Earth's water that is stored in aquifers below the ground surface. An aquifer is a permeable rock or sediment body that holds water in its pore spaces. Groundwater always exists below the water table in the zone of saturation and is one source of fresh drinking water that can also be used for agriculture. Unconfined aquifers, also known as water table aquifers, are not overlain by a confining layer. The upper surface of the aquifer, called the water table, is directly recharged by infiltration from the surface. These aquifers are more susceptible to contamination and fluctuations in water levels due to their direct connection with the surface. On the other hand, confined aquifers are overlain by a confining layer, usually an impermeable rock or clay. The water in these aquifers is under pressure, creating what's known as an artesian system. Confined aquifers are recharged from specific areas where the confining layer is absent or permeable. They are more protected from surface contamination, but can be depleted if overpumped. Infiltration occurs when surface water, such as rainfall or snowmelt, seeps into the soil and moves into the pores and cracks of rocks. Water is pulled down into the soil by gravity and capillary action, filling up the air spaces between rock and soil particles. Infiltration is influenced by factors such as porosity, how much water the soil can hold, and permeability, how fast water can flow into the ground. Areas with vegetation, low slopes, and warmer soil temperatures tend to have higher infiltration rates. As water percolates through the soil, it reaches the saturated zone, where the water table is located. When all the soil is saturated, excess water becomes standing water or runoff. The rate of infiltration is expressed in inches per hour and is affected by soil grain size, slope, vegetation, and rainfall intensity. Some materials, like granite, are impermeable and allow almost no infiltration, while others, such as limestone and sand, have high permeability and can hold large amounts of water, sometimes creating underground aquifers. Once groundwater enters an aquifer, it continues to move. It flows through the aquifer, driven by differences in elevation. Groundwater moves from areas of high elevation to areas of low elevation, following what is known as the hydraulic gradient. The journey of groundwater begins with recharge, which is the addition of water to the aquifer, typically through infiltration from the surface. As groundwater flows through the aquifer, it eventually makes its way to discharge points, where it leaves the aquifer and enters surface water bodies. All water added as recharge eventually finds its way into streams and rivers. This process is especially important during dry seasons when groundwater discharge plays a vital role in sustaining stream flow. Without this continuous input from aquifers, many streams and rivers would run dry during periods of little or no rainfall. Groundwater flow is controlled by a combination of factors that influence the movement of water through aquifers. One of the primary factors is the hydraulic gradient, which is the difference in hydraulic head between 2 points. Water flows from areas of high hydraulic head to areas of low hydraulic head. Permeability also plays an important role in groundwater flow. Permeability is the ability of a material to allow fluid flow, while hydraulic conductivity is the ease with which water can flow through a material. These properties depend on the size, shape, and connectivity of pore spaces in the aquifer material. Earth scientists use wells to measure energy at different locations. Hydraulic head is a measure of the total energy of a fluid at a given point, consisting of 3 components: the elevation head, the pressure head, and the velocity head. Elevation head represents the height of the point above a reference level, usually sea level. Pressure head is the height of a water column that the pressure at the point can support, while the velocity head, which is often negligible in groundwater, represents the energy due to the fluid's velocity. Hydraulic head is measured in units of length, such as meters or feet. The hydraulic gradient, on the other hand, is the change in hydraulic head over a given distance in the direction of groundwater flow. It represents the driving force for groundwater movement and is calculated as the difference in hydraulic head divided by the distance between 2 points. The hydraulic gradient is expressed as a dimensionless ratio or as a percentage, with steeper gradients indicating faster groundwater flow. Porosity and permeability control the behavior of groundwater. Porosity refers to the fraction of a rock or sediment that consists of open spaces or pores. It determines the amount of groundwater that a rock can hold and typically is expressed as a percentage or decimal fraction. Permeability, on the other hand, is the ability of a rock or sediment to allow groundwater to pass through it. Materials with high permeability, such as sand, allow groundwater to infiltrate through them, while low permeability materials, like clay, can impede groundwater flow. It's important to note that high porosity does not always indicate high permeability. For groundwater flow to occur, the pore spaces must be interconnected. A classic example is clay, which has high porosity but low permeability due to its small, poorly connected pores. Groundwater discharge is the process by which groundwater emerges from the subsurface and becomes surface water. This can occur naturally through springs, seeps, or as base flow to streams and rivers, or artificially through wells or drainage systems. Springs are a particularly interesting form of groundwater discharge, as they represent focused points where groundwater flows naturally to the surface. Springs occur where the water table intersects the land surface or when groundwater is under sufficient pressure to rise above the surface. Springs are important for providing base flow to streams and rivers and serve as an important water source for human use. When it comes to accessing groundwater, two main types of wells are used: ordinary wells and artesian wells. Ordinary wells, also known as water table wells, tap into unconfined aquifers where the water level in the well is the same as the water table. These wells require a pump to bring water to the surface and are recharged through the direct infiltration from the surface. On the other hand, artesian wells tap into confined aquifers where the water is under pressure. In some cases, the pressure is sufficient to cause the water to rise above the top of the aquifer and even flow naturally to the surface without the need for pumping. These are known as flowing artesian wells. Recharge in artesian systems occurs in specific areas where the confining layer is absent or permeable. The main difference between ordinary and artesian wells lies in the pressure differences. In ordinary wells, the water level is determined by the elevation of the water table, while in artesian wells, the water is under pressure due to the presence of a confining layer above the aquifer. Artesian wells are typically deeper than ordinary wells, as they must penetrate the confining layer to access the pressurized aquifer. However, this also means that artesian wells are generally better protected from surface contamination due to the presence of the confining layer. Like other hazards that we've discussed this semester, groundwater is also subject to various hazards that can threaten both the quality and quantity of this precious water supply. One of the most significant hazards is contamination, which can originate from point sources like leaking underground storage tanks or industrial spills, or from non-point sources such as agricultural runoff and septic systems. Persistent contaminants, including nitrates, heavy metals, and organic compounds, can remain in groundwater for long periods, making remediation, or purifying the water again, a challenging task. As groundwater is removed from the aquifer, the water table drops, which can result in increased pumping costs and even well failure. Overpumping also reduces the amount of groundwater stored in an aquifer, limiting the availability of this resource for future use. In some cases, it can take years or even decades for an aquifer to recover from the effects of overuse. The lowering of the water table due to overuse can also lead to the drying up of shallow wells and springs, reduced base flow to streams and rivers, and the degradation of groundwater-dependent ecosystems. In coastal areas, overuse can increase the risk of saltwater intrusion, where seawater is drawn into the aquifer, contaminating the freshwater supply. Subsidence of the ground is a serious problem in North America. This lowering of the ground surface is caused by a variety of human activities, including extraction of groundwater. Land subsidence occurs when the ground settles due to changes in fluid levels underground. Because subsidence occurs across large regions, its effects are less obvious and dramatic than those of sinkholes and karst landscapes. Nonetheless, subsidence also causes considerable damage. Small fractures can cause some areas to drop more than others, damaging homes and utilities. This can also cause fissures to form due to differential subsidence or uneven subsidence between two nearby areas. In coastal areas, subsidence can sink communities closer to the sea level and leave them more vulnerable to flooding. Subsidence is the event that occurs when portions of the land begin sinking. This can occur when large amounts of groundwater, and sometimes also oil, are extracted from an area. The rock and ground material underneath the surface of Earth that was once saturated loses that water as groundwater is removed. If the removal is not planned in a timely manner, it can be done too quickly and result in the area not being able to replenish itself. This causes the land sinking to begin. An example of subsidence can be seen in the San Joaquin Valley. The semi-arid Sacramento-San Joaquin Valley of Central California is known for its agricultural products, from citrus fruits and wines to grains, cotton, and rice. The area produces a quarter of the food in the United States. Heavy pumping of groundwater for crop irrigation has lowered the water table, causing more than 9 meters of subsidence in some areas of the valley. That subsidence threatens agricultural production, large water supply lines to major metropolitan areas, and important ecosystems. The marks on this utility pole indicate the level of the surrounding land in preceding years. Between 1925 and 1975, this part of the San Joaquin Valley subsided almost 9 meters because of the withdrawal of groundwater and the resulting compaction of sediments. After pumping by a nearby irrigation well forms a cone of depression, material from a leaking septic tank begins to flow into the home well in response to a new local slope of the water table. This is one of the ways in which groundwater can become contaminated by human activity. Groundwater contamination is a serious issue that occurs when pollutants enter the groundwater system, making the water unsafe for drinking or other uses. It can have significant impacts on human health and the environment. Contamination can come from various sources, including point sources like the leaking storage tanks or septic systems, non-point sources such as agricultural runoff or urban stormwater, and even natural sources like geologic formations that release contaminants. Contaminants can take many forms, from microorganisms and nitrates to organic chemicals, heavy metals, and radioactive elements. Once in the groundwater, contaminants can move with the flow of water, spread out, and become diluted, attach to soil particles, or even be broken down by chemical or biological processes. The consequences of groundwater contamination can be severe. Drinking contaminated water can lead to acute or chronic health effects, while contaminated groundwater discharging into surface water can harm aquatic ecosystems. Contamination can also render groundwater resources unusable for drinking, irrigation, or industrial purposes. Cleaning up groundwater contamination can be particularly challenging due to the inaccessibility of aquifers, slow flow rates, and complex interactions between the contaminants and the aquifer materials. These factors can make remediation efforts time-consuming, costly, and technically difficult. Finally, this is a different type of groundwater contamination. Heavy pumping in coastal areas can cause encroachment of saltwater and threaten the supply of fresh groundwater. Before pumping, in the image on the left, fresh groundwater forms a lens below the ground. If the fresh water is pumped out too fast, saltwater from below is sucked up into the well. Next, we'll discuss information that you'll need to complete this lab. There are no safety concerns specific to this lab, but be sure to wash your hands with soap and water after handling lab equipment. Be sure to pay attention to the units on the quiz questions. You'll be split into groups today, so make sure you're working together effectively. For this lab, you'll need a well opener, beep tape, and a clipboard with a map. You can bring gloves if you choose to. Additionally, worksheets and procedures will be provided by your TA, but will also be available on the instruction page in this week's Carmen module. If you're completing this lab in person, please be mindful of our supplies. We only have a limited number of beep tapes, and they are kind of expensive, so make sure you're treating them gently and they come back to us in the same shape that they left us in. The procedure and worksheets will be provided by your TA, but these will also be available in the instruction page in this lab's Carmen module.